If you remember, we talked about polarity in bonds back in chapter 9, but polarity also comes into play when we're looking at full molecules. So for a molecule as a whole to be planar, it needs to have those polar bonds that we talked about, which means there's an electronegativity difference, and we can measure a dipole moment. And remember, the atoms to look out for are oxygen, fluorine, chlorine, and nitrogen are the big ones. And in addition to that, they need to have an unsymmetrical shape. So that's what we're going to be looking at, understanding in this section, that unsymmetrical shape. Polarity is important because it affects the intermolecular forces of attraction, which affect things like boiling point and solubilities, that sort of thing. The non-bonding pairs, so lone pairs of electrons, are going to affect polarity. They're going to have kind of a negative end to them and pull other things towards them. Okay, so molecule polarity. If we look at just a simple molecule, hydrochloric acid, the bond between the H and the Cl is polar, and so the electrons get pulled towards the chlorine away from the hydrogen. We get the polar molecule. But what happens when our molecules become more interesting in 3 dimensions? What we need to do is be able to add dipole moments to understand if a molecule is polar or not. So if we have a linear shape and the bonds are the same in both directions, you can think of it as pulling in equal and opposite directions, which means there's no net dipole. If a molecule is trigonal planar and is pulling equally in 3 directions, there's no net dipole. But if it's trigonal pyramidal, you have this spot up here that's different from the others, and so that can be, they're not going to cancel out. You're going to end up with a net dipole. A bent molecule, if the 2 bonds are pulling with the same strength, you're going to get a net dipole because they're not in opposite directions. And tetrahedral, if you have these 4 identical bonds, then they're all going to cancel each other out and be nonpolar. Let's look at some examples. We have carbon dioxide here. Now this carbon-oxygen bond is polar, but because the shape is linear and the vectors are pulling in equal and opposite directions, that means there is no net dipole. It is a nonpolar molecule. If you think about that lining up in an electrical field, there's no specific way for this molecule to line up. No net dipole. But water, on the other hand, our 2 bonds here are polar, and we have these lone pairs up here that are pulling our electron density that way. So we have a positive charge down by the hydrogens, and we do end up with a polar molecule because the electrons are being pulled up toward the oxygen end. So if you want to predict polarity, draw the Lewis structure, think about the molecular geometry, then think about if the bonds in the molecule are polar. If there aren't any polar bonds, the molecule is nonpolar. So if it's, all carbons and hydrogens, you're not going to get a polar molecule. And then determine if the polar bonds will add together to get you a net dipole. Let's work through an example. Predict whether ammonia is a polar molecule. First, we have to draw the Lewis structure, determine its molecular geometry. So the Lewis structure is drawn over here. We have nitrogen in the middle with 3 hydrogens and a lone pair. We have this trigonal planar molecular geometry. Next, determine if the bonds are polar. Well, nitrogen is one of those ones that I told you to look out for. The nitrogen-hydrogen bond is polar. So we have to keep going. Finally, our shape if we look at it, we have this lone pair up here that's slightly different, and so we're going to end up with a net dipole because the bonding electrons are pulled slightly towards the nitrogen end of the molecule. So ammonia is a polar molecule. Next, some practice. Decide whether the following molecules are polar. So our first molecule here, we have the Lewis dot structure drawn. Our geometry around our nitrogen is bent. So really our molecule looks something like this. And we do have polar bonds here. The slightly polar bonds. This molecule is going to be slightly polar, not nearly as polar as something like water, but it is slightly polar because of its bent structure and the polar bonds present. Our sulfur trioxide here, we have our geometry around our sulfur. We have 3 bonds, no lone pairs. And so our actual geometry here is something like this. And remember, this is going to be a resonance structure, so these 3 bonds are equal to each other. And then everything is equal, pulling in directions that cancel each other out. It's symmetrical, so this is going to be nonpolar, even though it does contain polar bonds. Okay, multiple choice for you here. Which of the following molecules is the most polar molecule? Okay, so they all have the same atom in the middle, so we're just comparing our halogens on the edges. So would be most polar with all bromines, all chlorines, all fluorines, chlorine top and bottom, bromines on the side, bromines top and bottom, chlorine on the side. Now anything top and bottom is going to cancel each other out because they're pulling in equal and opposite directions. So it's just this middle part here that we're worried about, and the most polar of the middle. So you can see here, once you have it narrowed down to you're worried about the middle, well, A and D are the same. B and E are the same. So that leaves you with the answer of letter C, and that makes sense because fluorine is the most electronegative atom, so it's going to be the most polar out of these. Now, why do we care about polarity? It affects molecular properties like solubility in water. So polar molecules are attracted to other polar molecules because their negative sides are attracted to the positive side of another molecule. And that means that because of those attractions, polar molecules are going to dissolve well in other polar molecules because they all line up with these positive and negative sides. And non-polar molecules that don't have these dipoles are not going to dissolve well in polar molecules like water. So the general rule is like dissolves like. So if there are dipoles present or charges like ionic compounds, they're going to dissolve well in each other. Non-polar molecules don't dissolve well in them. But some molecules can have both polar and non-polar parts. The example is soap. So soap has a polar head that will attract water and this long carbon-hydrogen tail that will interact with grease, oil, that sort of thing. And what happens in 3 dimensions is soap molecules line up and form these micelles that have the polar heads all around, and again it comes in 3 dimensions, so you can imagine it like a ball, and the inside of it is all non-polar, and so it can trap grease molecules in the nonpolar part, and then the polar part can get washed away with water. So that's why soap works well to wash away grease. It works well to wash away, say, small viral particles, because many of them have a lipid bilayer, so they have this nonpolar parts surrounding their proteins and DNA or RNA. And so soap works well to wash all of that away by attracting the nonpolar parts, surrounding it by something that is polar that can then be washed away with water. Whereas if you've ever tried to, say, you get oil on your hands and you just run water over it, you notice the water and the oil, they don't interact well. The water doesn't do anything until you add the soap to it.